In the previous video, we talked about molecular orbitals, and if overlap of close-by atomic orbitals to make molecular orbitals was all there was to making orbitals, then there really wouldn't be much to organic chemistry. What makes carbon atoms so versatile is something called hybridization. All right, which is, and I'm gonna go ahead and admit that this concept is a little can be a little bit abstract, but it's fairly important because it explains why carbon can bond in so many different ways. All right, so first of all, I'm going to start off with in introducing this topic by going back to a very simple molecule and talk about something that, if you think about it, doesn't really make sense. All right, so this is methane. And what we know about methane is it's a carbon that's got 4 hydrogens connected to it. And we know a lot about methane. It's a very simple molecule. But one thing that we know about it is that all of these bonds are equivalent to each other. All right. So this is a tetrahedral molecule. All right. So this bond and this bond you can think of as being in the plane of the paper. This bond is going to the right, but it's coming out towards you. This one is going back away from you. So you can think of these 3 hydrogens as if they're the legs of a tripod. All right, and this is just something sticking straight up out of the tripod. All right, and every single one of these bonds is just like the other. In fact, you could take this thing and you could turn it around and it would look just like itself. All right, and these bonds are every bond is exactly 109.5 degrees. That's the bond angle of a tetrahedron. So here's the issue. Back in introducing atomic orbitals, we talked about electron configurations, and this would be the electron configuration for carbon. All right, and we could take that electron configuration and we could do an orbital notation like this, where you could represent so again, the further you go up, the higher the energy of the orbital. We could show 2 electrons in the 1s orbital. And again, they would have different spins, all right, represented by the different directions of the arrows, all right. And then we get to this 2p level, and we have 2 electrons in different p orbitals, and they're both spinning in the same direction, all right. So the thing about this is that if we were to look at this orbital notation, and knowing that covalent bonding occurs when electrons share, when atoms share electrons. All right. Well, this would indicate that we've got a single unpaired electron in this orbital and a single unpaired electron in this orbital. All right. So it looks like you would only be capable of making 2 bonds to the carbon. All right. So how is it that we have a configuration like this, which looks like we would only be able to pair up 2 of these electrons, when we know that carbon makes things that can pair up with at least 4 different atoms? All right, so how do we get from this, where it looks like 2 of these valence electrons are already paired and 2 of them exist as single, to basically representing it as something as if all of these electrons are equal? All right, and it has to do with this concept of hybridization. So the concept of hybridization goes a little bit like this. All right, so if we take the original, orbital notation of the single carbon atom, all right, and what we're going to do is we're going to do what's called promoting an electron. All right, so we're going to take one of the electrons from this 2s orbital, and we're going to promote it up to the 2p level. All right, so we would then have this. All right, and then what is described as happening is you have this thing called hybridization. All right, so this is a little bit conceptually difficult, but essentially what happens is you have one s orbital and 3 separate p orbitals, and they're going to combine to make 4 separate orbitals that are kind of this hybrid type orbital that has some s character and some p character. All right, and so a quick way to describe that is to say, well, this is an s orbital right here, Obviously, it's perfect. It's just a ball. It's perfectly symmetrical along an infinite number of axes. All right, and this is a p orbital, which looks kind of like a dumbbell. All right, and if these things were to combine, let's bring these guys together. Well, something that is like this is a kind of like a p orbital. It's got two lobes. All right, but when it overlaps with that s orbital, it's going to make one of the lobes a little bit bigger. All right, and so this is the shape of what's called an sp3 hybrid orbital. All right, and every single one of these orbitals would look exactly like this. All right, so what would be the difference between these orbitals? It's going to be the orientation. All right, so if you took 4 of these, you could arrange them so that they overlapped with each other, so that the skinny, this is called the node of the orbital, was right there in the middle. All right, and just to give you a little orientation, that's where the nucleus of the carbon would be. All right there in the middle. All right, so note that when I drew this, I'm not showing the 1s orbital. All right, remember there is still this 1s orbital. That would be basically a ball that's about right here. I'm not drawing it just to keep things a little cleaner. All right, so this right here would represent a carbon that's got 4 sp3 orbitals. All right, notice these are all orbitals that are in the second level. All right, so therefore they would all be considered, these would all be valence level orbitals. All right, so if we take that and then let's say, so remember we're trying to make methane here. So we also have 4 hydrogen atoms. All right, well, a hydrogen atom is just 1s1. That's its configuration. So it's just got an s orbital. And what if we took 4 of these s orbitals and put them at the tips of each of these sp3 orbitals? All right, that would allow for a sigma bond to get formed between each of these orbitals and that s orbital, and that's what this shows right here. All right, the only difference between this and this is that this is going to get extended out a little bit longer when it overlaps when that s orbital. All right, and again, the reason that it's considered a sigma bond is that when you if I take this and I put it up here, all right, notice that that's a head-to-head type of arrangement between the orbitals. So all of those would be considered sigma bonds. So if I wanted to do a model of sp3 hybridization, all right, this would be an sp3 hybridized carbon. All right, and the one thing to notice about it is that all of those bonds are the same. All right, so again, this shows the tetrahedral arrangement. So notice no matter how I twist this thing, it's always going to look the same. All 4 of these things are exactly equal to each other. All right, and to make this into a methane, all I have to do is, if I consider this ball to be a little hydrogen atom, is if I put it at the tip there would be overlap between that sp3 orbital and the s orbital of the hydrogen, and that would make that sigma bond, which is the bond between the carbons and the hydrogens. So sp3 hybridization is the type of hybridization you're going to have whenever you've got 4 single bonds to a coming off of a carbon. All right, but we know that there are sometimes double or triple bonds. All right, and so those have different types of hybridization. All right, so the next type of hybridization is what's called sp2 hybridization. And that's actually a typo right there. The 2 should appear as an exponent. All right, so again, what we're going to do, we're going to be starting off with, we're going to be doing a little shortcut. We're going to start here after a single one of those electrons has been promoted. And by the way, this little exercise that I'm doing right here, where I talk about an electron being promoted and then hybridized, this isn't something that actually happens when these molecules are made. All right, it's almost like we're talking as if we had a bottle of neutral carbon atoms laying around, which doesn't really exist. But we're doing this little mental exercise to explain kind of how the hybrid orbitals work. Keep in mind that this actual process doesn't occur when these molecules are formed. All right, so again, if we start at that step where we've mentally promoted an electron from here to the p level, all right, We're then going to hybridize it, but instead of having 4 equal sp3 orbitals, one of these p orbitals is going to remain unhybridized. All right. And one thing I want to point out here is that the energy level of these hybrid orbitals, notice how they're in between the energy levels of the s and the p. All right. So here you're going to get 3 what are called sp2 hybrid orbitals. Notice that the energy level is somewhere between the s and the p levels. But then you still have this p. One of these guys remains unhybridized. So it's still going to exist as a p orbital. All right. So what is that going to look like? So each of the sp2 hybrid orbitals is going to look pretty much like one of these sp3 hybrid orbitals. The big difference is going to be what happens when they come together. So again, we only have 3 of these, and when those come together, they're going to come together kind of like this, like where this right here is one of them, right? This right here would be another one of them, and here's the third. And they're going to end up making something that has a trigonal planar orientation. All right. So notice that this right here looks kind of like the drawing that you have down here. And the thing about this is if you look at it on its side, it's totally flat. All right. So what we're going to do, as we said, this is going to involve 3 of these guys, but it's also going to involve this unhybridized p orbital. All right. So if I take a p orbital, which looks kind of like this, if I hold these guys end to end, all right, what I'm going to do is if I take that and I turn it so that you're looking at it straight on like this, that's what you're seeing right here. All right, where this front one would be the one that's closer to you, and then but we know that back behind it there's the back end of that p orbital, and that's what I'm trying to show here. All right, so this is a little bit hard to draw because we're trying to do something which is 3-dimensional, but what ends up happening is if you have that original, actually let me increase the size of this. All right, so if you take this original, just the sp2 orbitals, and then you essentially take one lobe of the p orbital and put it here, and you take another lobe of the p orbital here, okay, you end up getting this right here. All right, and I can kind of spin that around. All right, so my fingers are touching the p orbital, and these would be the 3 sp2 orbitals. All right. So sp2 orbitals are going to be involved anytime that you have double bonds between carbon atoms. So the simplest example you can think of would be ethene. It's also called ethylene. All right, and this is its structure. All right, so what I have here, I have two separate sp2 hybridized carbons. All right, and the parts that I'm holding right here, I'm holding onto those unhybridized p orbitals. All right, so you can see in this orientation it's trigonal planar, but in this orientation right here you can see those p orbitals. And what's going to happen when you make this molecule is, first of all, 2 of those sp2 orbitals are going to overlap. All right, so if I show it like this, you can see 2 of those sp2 orbitals overlap, and when those 2 atomic orbitals overlap, they're going to end up making this molecular orbital. All right, so this thing in between, that is now, it would not be lopsided like this. Picture this thing right here as being, this middle bond as being symmetrical between these 2 atoms, but that's the bond that gets made. All right, and that essentially is what one of the 2 bonds are. All right, so we know that there's 2 bonds. So where's the other bond between these 2 atoms? It has to do with these p orbitals. All right, notice that these p orbitals are kind of arranged in a way that they're side by side with each other. All right, and so what's going to end up happening is you're going to get a little bit of electron sharing as these p orbitals can share electrons with each other. Okay, and so that's what I'm showing here. All right, you've got these p orbitals that are now side by side, and they're going to share electrons. All right, so therefore that would be a pi bond. All right, it's the side by side type of overlap. All right, so even though